So we're going to wrap up the Dirac equation that we've seen in the past 2 weeks. So what did we notice? Well, we noticed that it solves some of the problems of the Klein-Gordon equation, but certainly not all. We can make sense of negative energies through the Dirac sea, so by occupying all negative energy states, and in this way disallowing any single particle excitations to drop to the very negative energies. But clearly this only works for fermions, and we know there are also bosons in nature. And anyway, to make sense of a Dirac sea, we have to be able to describe multi-particle systems. So we're going to try something else. We're going to we gaan het over een andere boeg gooien, as we would say in Dutch. But before that, we still have to wrap up some of the successes of the Dirac equation, because of course we've not spent these lectures on a failed attempt at doing quantum mechanics of fermionic particles. It's just that soon we'll have to actually reinterpret what this Dirac equation really means. So let's finish the success story, which was the main support of that there is some physics in the Dirac equation, and this was in the setting of the Dirac equation in the electromagnetic field. So recall that we obtained the proper Dirac equation when electromagnetic fields are present via the minimal substitution, where you shift the potential by, you shift the momentum by the vector potential and the energy by the scalar potential of the magnetic field. Minimal substitution. And there will be an exercise on Monday where you're really going to check that this is the proper way to incorporate the electromagnetic interaction in a minimal coupling, such that, for instance, the Lorentz force on this charged particle is really represented well by this particular equation. And in order to get something that we can compare it to experiment, it's useful to go to a non-relativistic limit. So how do we do this? Well, the convenient way is to take your 4-component Dirac spinner and write it as two component spinners, because you should remember from your previous quantum mechanics courses that the spin 1/2 particle is usually described by 2 components, and one for the spin up and one for the spin down part. So somehow we have to make sense of what the other 2 components are actually doing there. Now we've already seen that 2 of these components actually correspond to the wrong negative energy solution. So let's see explicitly how this comes about. Okay, we have here simply a Schrödinger equation if you would take out the time derivative. And if we assume that our electromagnetic field is static, then this is a time-independent Schrödinger equation. This, the Hamiltonian, is time-independent. So the first thing you would do in order to find the solutions there is to look for solutions of the time-independent Schrödinger equation. So we set our wave function psi equal to spatial dependence times kind of the uniform phase in time, and then you get the explicit time-independent Schrödinger equation corresponding to this Dirac equation. Now, if you recall from the beginning of the lecture 2 weeks ago, this Hamiltonian is written in terms of these matrices alpha and beta, and they have Pauli matrices in them. in their blocks. So if we write out this equation in terms of the individual components, psi u and psi d, then we arrived last week at this coupled pair of linear equations on the wave function side. Okay. And in order to take the non-relativistic limit, we're going to say that the energy is given just by the rest mass energy plus some small non-relativistic kinetic energy that I'll denote by E and R. Now, writing out these equations, we already observed that the rest energy for the upper component actually cancels on both sides, but not for the lower component, because due to this beta matrix that we have in the Dirac Hamiltonian, there is a minus sign in front of the rest energy term. And this rest energy is a lot larger than the potential energy. And also, well, by assumption, the non-relativistic energy is much smaller than the rest energy there. So really the dominant components for the lower part come from the mc squared. So this means that we can solve this equation to leading order in this non-relativistic approximation as, well, in terms of the Pauli matrix, minus I h bar this, and then divided by the 2mc squared. Okay, one of the c's is cancelled with that one, so I have a 2mc here. In terms of the upper component. Now, if you look here, what is the order of magnitude of this, the lower spinor component compared to the upper one? For here we have the momentum, and we're comparing the momentum to mc. Right, so this is really of the order of the velocity of the particle over the speed of light. So this is the order of the velocity over the speed of light times the magnitude of the upper component. So indeed, this part is really suppressed if we're looking at particles that are not traveling fast compared to the speed of light. Now, this is also what we should expect from the explicit plane wave solutions that we've seen last time. So remember that if you look at the zero momentum solutions, they just corresponded to having non-zero values for the top two components and 0 for the lower ones. And then if you want to look at plane wave solutions that have, well, a small momentum, you have to do a small Lorentz boost, which does mix the upper half with the lower half. But okay, a small Lorentz boost to these off-diagonal components, they are proportional to the velocity v over the speed of light. So this is indeed what we would expect. So clearly, if you have very slowly moving particles, the two top components are the ones that you would usually see, and you would think of the lower ones as vanishing, being vanishingly small. But this is not entirely true. We cannot exactly neglect these two lower components, because if we now substitute this solution into the first equation, then we see that it's multiplied by the speed of light again. So we get the speed of light times v over the speed of light. So this term is really proportional to the velocity and is not, well, so it's not negligible. So let's write out the substitution. So we have that the non-relativistic energy times psi of u is now Q. We have the potential energy, and then this term here, which now appears twice by the substitution. Where we now see indeed that the speed of light cancels. So we certainly want to keep this this contribution. Okay. So let's work out what the square of this operator really is. And what can we use there? Well, we can use this nice identity that you can find in the appendix of the lecture notes, that if you have a Pauli matrix inner product with a vector times a Pauli matrix inner product with another vector, then we can expand it like this. So we have simply a scalar part multiplies the identity matrix. And then we have well, an imaginary part, if you like, that still multiplies the Pauli matrix, which depends on the cross product of these vectors. So if we plug this in, so the scalar part, so it will just give you the square of this. So it is minus IH bar gradient squared. And then here we get the outer product of this operator with itself, or the cross product of that operator with itself. Okay. Acting on psi u. Now, if these were just vectors, of course, the cross product of the vector with itself would vanish. But these are actually operators, and they do not commute with each other, because I have a derivative here, and here is a function, so I cannot pull this function through the derivative without getting something non-trivial. And indeed, if you just expand out this project, this product, we get the only non-vanishing contribution is this derivative acting on the vector potential. So here we get IH bar Q, and then the curl of the vector potential. And as you will remember, the curl of the vector potential, that is just the magnetic field. So here we can read off what the actual Hamiltonian is, the two-dimensional Hamiltonian that's acting on these two components. And this Hamiltonian is called a Pauli Hamiltonian. So we find standard kinetic term we have here. And then this term, so the i's nicely cancel to give you a minus sign. So yeah, QH bar and then Pauli matrix inner product with the magnetic field. And then there is still the scalar potential. So what we see is that we almost get the standard minimal substitution for the non-relativistic particle. So taking the momentum in the case of a particle without electromagnetic interaction, shifting it by q times the vector potential, and also shifting the Hamiltonian by q times the scalar potential. But there is this additional term. And this additional term is exactly the intrinsic magnetic dipole moment interaction that you would expect, because it's an operator sigma, so that's the spin of the particle, in our product with the magnetic field. So it's telling you that the spin will like to align with the magnetic field. So in this kind of the operator that you take in a product with the magnetic field, that is exactly the intrinsic magnetic dipole moment. So we read off here that it's of the form G over 2 QH bar over 2M. The Pauli matrix, where G is now exactly equal to 2. So what does this mean? It means that if you start with the relativistic minimal substitution in the Dirac equation, then you take the non-relativistic limit, you get exactly the minimal substitution of the spin 1/2 particle, but together with this magnetic dipole interaction. It just follows out from there, taking this limit. Now in the lecture notes, some more corrections, relativistic corrections are discussed. This is not exam material, but take a look. Certainly read it as background material. So for instance, you can compute further velocity over the speed of light corrections, and also the interaction of your spin, not with the background magnetic field, but with the magnetic field that is actually generated by the orbital velocity of your charged particle. So if you have an electron in a hydrogen atom, it's going around your nucleus, and therefore producing its own magnetic field, which should couple to the intrinsic spin. So that's the spin-orbit coupling that you can also derive from the Dirac equation. And these are all very well tested experimentally already, well, back in the old days. Finally, quick remark. So we saw in the beginning that G is not exactly equal to 2. You have G minus 2 is actually experimentally measured to be something like 0.0023. So where do these corrections come from? Well, they are not from further relativistic corrections. They actually come from quantum electrodynamics. Meaning quantization of the electron field interacting with the electromagnetic field. So you can never derive these numbers from just looking at free particles like we're doing here. So this is really an interacting correction term. And okay, this is one of the best tested numerical values in the history of physics, because you can compute these to like 8 digits in quantum electrodynamics, and they're also measured to about 8 digits, and they agree. So this is also one of the nice places where people look for signatures of new physics, because even if new physics would have only a very small effect on this anomalous intrinsic dipole moment, since it can be measured extremely accurately, you still may have a chance of finding such effects there. Okay, this wraps up our discussion of the Dirac equation. Are there any questions about this or what we talked about last week? Seems not. Okay, so let's move on to the next topic, also next chapter in the lecture notes. So what are we going to do? Well, we've seen that naively adapting the Schrödinger equation to a relativistic wave equation, it leaves us with some problems, negative energies, that we do not quite know how to deal with multi-particle systems. In the case of Klein-Gordon, we also do not know how to give a probabilistic interpretation. So we're going to take a step back now and think of a wave equation that we understand very well, or we know how to interpret very well, and that is manifestly satisfying the relativistic principle. And what is this wave equation? Well, it's simply electrodynamics, the Maxwell equations in vacuum. So what we're going to do now is go back to classical physics, classical electrodynamics, convince ourselves that Maxwell equations actually give an example of a relativistic wave equation, and then see what actually the consequences are for quantum physics. Okay? So we've already encountered some electromagnetism here in the coupling of the Dirac equation with the electric and magnetic fields. Now we'll take a slight step back and be a bit more careful about how these potentials arise from the Maxwell equations. Also to refresh your knowledge a bit. The Maxwell equations, let's just recall them. And introduce the quantities again. So the electric field we denote by the curly E, not to confuse it with energies. Magnetic field B. We have a charge density rho. Let's denote rho with subscript C to differentiate it from the probability density that we've seen before. And then let's say just current density J C. And let's write down the four Maxwell's equations. So first we have the Gauss law for magnetism, which says that the divergence of the magnetic field vanishes if we don't have any magnetic monopoles. Faraday's law which says that the curl of the electric field agrees with the time derivative of the magnetic field. So this we experience very well in our electromotors. The Gauss law for the electric field, which says that the divergence of the electric field is related to the charge density. So that is really Coulomb's law in electrostatics. And finally, we have Ampere's law states that the curl of the magnetic field is related to the time derivative of the electric field. Plus the current density. So let's just recall the names of these constants here. So this is the permittivity. And this mu0 is the permeability. And they're related to the speed of light through 1 over c squared being equal to the product of these. Okay, so we have 4 equations here, but we'd like to see one wave equation. So we certainly want to bring this back to a simpler form for our purposes. So what is the first step that we always do to get rid of 2 of these equations? Well, it's by introducing a scalar potential and a vector potential that we've already seen last week. Maybe let's just do a quick poll here. So please open the app again. So just to refresh your mind, so which laws can be eliminated by changing your description to the scalar potential and the vector potential? Do you remember? Let's see. Okay, opinions are divided. Okay, I'll leave it open and then we'll just see what happens. So let's recall again how the electric and magnetic fields are related to these potentials. So I wrote this down last week as well. So we can find the scalar potential phi and the vector potential A such that the electric field is given by the divergence of the scalar potential minus time derivative of the vector potential. The magnetic field is just the curl vector potential. So which of these equations are automatically satisfied when I express the electric field and magnetic field in this way? So for the second case, maybe that's the easiest. So if the magnetic field is the curl of a vector potential, then, well, what do we know? The divergence of the curl, it vanishes, right? So certainly this one here is automatically satisfied. So Gauss' law for magnetism should be at least 1. Okay, well, we're getting closer. So how about the first one? So which equation is automatically satisfied there? So I have a gradient. So the curl of a gradient is automatically 0, right? Okay, but then I still have this derivative, so minus the curl of the vector potential, but that is the magnetic field. I see some people are shifting votes. Ah, very good. Yes, okay. So it was the Gauss law for magnetism and Faraday's law. Now I'm gonna stop the poll. Now everybody is on the same page now. Very good. Yeah, so not only if we express the um, the magnetic field and the electric field in terms of these potentials, they are automatically satisfied. Also, conversely, if we're on a simply connected domain, so on say the whole four-dimensional space or three-dimensional space plus time, then if you have a magnetic and electric field satisfying these equations, then you can always find scalar potential and a vector potential such that this expression holds. So that is nice, and that's why it's much more convenient to work with these potentials instead of with the fields directly. Okay, so let me just write this down. So using phi and a, the first two are automatically satisfied. So we only have two more equations that we have to impose. Now already last time we noticed that it's useful to actually group these two potentials into a four vector. Right, so in order to find a covariant form for the Maxwell's equations, we're gonna look at the four vector potential. A mu, where the time component is really the scalar potential, and the spatial components are the vector potential. And we have put a speed of light there to make the units agree. Now, on the right-hand side of these equations, we also have the charge density and the charge current. So let's also group those into a four vector. So we also introduce the four current, J mu, charge current being this. And let's see what these, the Gauss law and the Ampere's law look like when I express them in terms of these four vectors. Okay, so Gauss law. So we have 1 over the permittivity times the charge density should be equal to the divergence of the electric field. So then we can simply plug in this expression. Let's write the vector potential first and swap the time derivative and the spatial derivative. So we get the divergence of the vector potential minus divergence, the gradient, scalar potential. So we want to kind of rewrite these derivatives in terms of the covariant derivatives with four indices. So let's do this for both terms in such a way that Okay, we have here a time derivative, and then we have a spatial derivative, but then we would also like to have another time derivative there. So we have to add another term. So let's just simply add it and subtract it again. So we put a, right, so this is the spatial derivative of the spatial component of the for potential. So we also want a time derivative of the time component of this potential. So we really want to add the, let's write it, this, where I have a 1 over c coming from this c, and another 1 over c such that this becomes the x0 coordinate. This is kind of the combination that we would like to see. So if we then, again, add this term here, this, second derivative, because we have two time derivatives, and here we have the gradient squared, so that's just the Laplacian. Then we have kind of two terms that look a lot more covariant already, because if I now just write this in index notation, so this is just the zeroth component of the forecurrent. I have to compensate with an extra c. Well, okay, I'm dividing by an extra c. Then I get here minus c d0 component. Let's take a new d nu. Okay, a nu, and here I have d nu, the a0 component. So I've taken the c squared here, it combines into the nu equal to 0 part. Okay, and then for Ampere's law, we have, okay, so let's write the, let's take this, the electric field part to the other side. So we get that u0 is the rotation, the curl, magnetic minus c 1 over c squared time derivative. Okay, so now we have the curl of the vector potential plus the second time derivative of the vector potential plus 1 over c squared d squared by dt squared. And then a time derivative of the gradient of the scalar potential. Sorry. So let's write out the curl of the curl. So we can also write this as the gradient of the divergence minus the Laplacian acting on the components of the vector potential. So what do we get? This is the gradient of the divergence of A, but here I also had a gradient of the time derivative of phi. So plus 1 over c squared. Sorry, time derivative. And then for the other terms, I have the second derivatives minus Laplacian. So if we now write this again in index notation, this is really the, okay, so this is the partial derivative with respect to the ith component. Here we again have the same four divergence of the 4 vector. So d nu a nu, and then the the D'Alembert acting on, okay, not vector but AI, like this. So we see that in terms of the 4 vectors, these equations are really the same. So we read off the covariant Maxwell equation in this form. So we have the D'Alembert acting on this 4 potential minus the 4 gradient of the 4 divergence has to be equal to the permeability times the 4 current. Okay, that looks already a lot better. We now have a single equation. Let's just make a quick remark here. What happens when I take the 4 divergence of the left-hand side of this equation? So if I write out the D'Alembert again as d nu a mu, then I see that this is really the D'Alembert acting on the divergence, the 4 divergence of A, and here I also get the D'Alembert acting on the 4 divergence of A. So these terms are really identical. So this vanishes, and it means that the right-hand side also vanishes automatically. So the 4 divergence of the 4 current has to be 0. Now this is exactly a continuity equation as we've seen it for the probability density, except now it's for the charge density. So this is the continuity equation. Which really says that there is conservation of charge in your system. Any change in the charge density has to be compensated by a charge current that moves the charge somewhere else. Now from here on out, we're only going to look at electromagnetic fields in vacuum. So no charged particles present. So we're going to set J mu equal to 0. And the equation that we then get is what we call the 3 electromagnetic field equation. free electromagnetic field. So in the exercises, you're really going to check that this field equation satisfies the relativistic principle. Well, of course, we have to transform the vector potential in the appropriate way. But the placement of the indices already kind of tells you how it should transform as a contravariant vector field. Contravariant vector field. So what does this mean for the spin of the particles that are described by the electromagnetic field? Let's do a quick poll again. So remember, how is the relativistic principle going to tell us what the spin of a particle is? Well, we've just told ourselves how to transform this field under a Lorentz transformation, so in particular under a rotation. So we're essentially asking, by how much do I have to rotate this field in order to get back to the identity again? If I have to rotate it by 4 pi, like in the Dirac equation, then I have a spin 1/2 particle. If I have to rotate it by 2 pi, I have a spin 1 particle. If I have to rotate it by pi, then I have a spin 2 particle. And if any rotation brings it back to the identity, then it's spin 0. So the question really is, how far do I have to rotate a vector for it to return to its original position? Let's see. The answer, okay, opinions are still divided here. So how far do we have to rotate a vector? By what angle for it to get back to its original position? Here's my vector. I rotate it by pi. Well, that's not enough, right? I have to rotate it by 2 pi. So rotation by 2 pi, that really corresponds to spin 1. So somebody, okay, yes. I think we can stop here. Very good. I think this is, okay, let me just write it down, record it before you change your mind again. These are spin 1 particles. So what are these particles described by the electromagnetic field? Well, let's say as soon as we quantize it, well, these are photons, right? So spin 1 particles. Photons. So that's nice. We've already seen spin 0. They have the Klein-Gordon equation, spin 1/2. You have the Dirac equation. Hey, and the Maxwell's equation, do spin 1 for us. Okay, let's continue at 4:30. Take some tea now. If you're ready again, I suggest we start. So we managed to reduce the number of equations from 4 to 2. Okay, and then we group these two equations into a four-factor equation. But this reduction does come at a cost, something that I'm sure you've encountered before. And this is the fact that this vector potential and the scalar potential are not directly measurable. So there is redundant information in these quantities. Or another way to phrase this is that the electric field and the magnetic field, which are directly measurable, you can just go out there and measure these fields, they do not fully determine this four potential A mu. In what sense? Well, in the sense that if I have some four potential A mu and I compare it to another four potential A prime mu that differs from the first one by a four divergence of some real function chi, it can depend both on space and time, they describe the same physics. Or to put it differently, they give rise to the same electric and magnetic fields. So written out in a non-covariant way, the vector potential, it transforms by the addition of the gradient of chi, and the scalar potential by the subtraction of the time derivative of chi. And indeed, if you take this and you plug it into our definition, then you see again the gradient, or the curl of a gradient vanishes, and here, well, the two terms cancel each other. So this is a redundancy that we have to live with and have to deal with. And the typical way to deal with this is by imposing a certain gauge condition. And we'll choose a particular one. So let's just say that we can always transform our four potential to satisfy, can always perform such a gauge transformation, as it's called, such that our vector potential satisfies the Coulomb condition. So this is the Coulomb gauge. What does that mean? It means that we require the divergence of the vector potential to vanish. So what is this saying? It is saying that if I have an arbitrary four potential A mu, I can always find a chi such that subtracting this and getting your transformed four potential A prime satisfies this equation. Now here I'm just dropping the prime because I'm imposing it on the fields that we're going to allow. So let's see what the consequence of this condition is by looking at the Gauss law. So the Gauss law in vacuum, so remember we're setting the charge density to 0. It says that the divergence of the electric field has to vanish. So what is the divergence of the electric field in terms of the vector potential and the scalar potential? Well, it's the Laplacian scalar potential minus the divergence of the time derivative of the vector potential, or the other way around, time derivative of the divergence. So this has to vanish, but in our Coulomb condition, this term already vanishes. So Gauss' law tells us that the Laplacian acting on the scalar potential has to vanish. So that is saying that the scalar potential has to be a harmonic function. And there is this nice property of harmonic functions that, for instance, you can find the value of a harmonic function at a position x by averaging all the values of this function on a large circle around x. So if we assume that the scalar potential vanishes at infinity or falls off sufficiently fast at infinity, then taking a sufficiently large circle, this average will also vanish. So having a harmonic function that falls off at infinity implies that the harmonic function is actually equal to 0. So if phi of rt goes to 0 as if you take the distance to infinity. So really, we do not only have that the divergence or the vector potential is 0, but this really implies that also the scalar potential vanishes. And this is one reason, and this is a very convenient gauge because it very much limits the degrees of freedom that I have. Oops. So what do our equations look like in this Coulomb gauge? So now our electric field is simply the time derivative or minus a time derivative, the vector potential. And the magnetic field is the curl, as usual. And how about the Maxwell equations? Let's see. We wrote them up here. Where we said we put the current equal to 0. And how about this term? So this is the 4 divergence of the 4 potential, but that has 2 terms. One of them is the divergence of the vector potential, and the other one is the time derivative of the scalar potential. But both of them vanish, so we're only left with this part. So really the Maxwell equation here is extremely simple. It's just a D'Alembert acting on the vector potential required to vanish. So this should already look somewhat familiar to you. This is saying that each component of the vector potential satisfies the Klein-Gordon equation. Well, not any particular Klein-Gordon equation, but the massless one. Equation with m equals 0. Now, of course, this is no surprise because we know that light travels at the speed of light, so the particles that it's describing better be massless. Let's do a very quick poll. Yeah, so each component of the vector potential satisfies the Klein-Gordon equation. Is the same true for the components of the magnetic and electric field? So if I apply the D'Alembert to the electric field, and I know that the vector potential vanishes, it's the D'Alembert acting on it. Then of course these derivatives, they are going to commute with each other. So automatically D'Alembert acting on this, well, that's the same as the time derivative of D'Alembert acting on A, but that is 0, right? And the same is true for the magnetic field. So we're again converging on a consensus. Very good. So the answer is yes. I was being a bit creative here with the reasons why the answer could be no. But it's a simple yes. Okay. Now here's another remark. Or no, let's not do a remark. Let's do another poll since we're here's. So does the wave equation in Coulomb gauge satisfy the relativistic principle? So again, what does it mean to satisfy the relativistic principle? If the equation holds in my inertial system, does it then automatically hold in yours? Let's see. Okay, we're again divided. Well, this is also a bit of a trick question, right? Well, we just said that the Maxwell equation satisfy the relativistic principle. So certainly the physics is going to be the same in our different frames. But this equation itself, well, and the Coulomb condition itself, it's clearly not relativistically invariant. This is not a covariant gauge because, well, my scalar potential vanishes. So if I boost to another frame, that mixes the scalar potential with the vector potential. So then it's not going to vanish anymore. So in that sense, one could argue that no, this does not satisfy the relativistic principle. But of course, the answer could also be sort of, because in some sense, how do I define the relativistic principle? It was saying that the physics is the same in each frame. Of course, if I transform my solution in this gauge to your frame, you can still do a gauge transformation on this solution to bring it back to the same gauge again. So it really describes the same physics. So I would say the correct answers are no or sort of. Very good. So let's summarize this. Oops. So this is a non-covariant gauge. We're singling out a special, well, we're giving a special role to the time component here. We could also have used a different gauge as opposed to, say, the Lorentz gauge. So that just requires that the for divergence vanishes. Note that this is also true in the Coulomb condition. So the Coulomb condition is really a stronger gauge condition than the Lorentz gauge. What is the advantage of working with this non-covariant gauge? It's because since we are imposing such a strong gauge condition, it's easier to read off the physical degrees of freedom. So, but the physical degrees of freedom are easier to read off here. Let's do another poll. We're doing well. So how many local degrees of freedom are there in the electromagnetic field? Well, either based on what you know, or based on this discussion. Just counting, well, how many local parameters can I change in the vector potential? Right. So our physical description is now a scalar potential and a vector potential, or if you like, the 4 potential. So there are certainly at most 4 degrees of freedom. But what is the real number of parameters that I can tune per space-time point? Well, we already said that we can put phi equal to 0, right? So we only have the 3 components of the vector potential. So 4 is certainly too much. But well, we also have this the divergence condition. So that's one extra condition. So we're removing 1 from the 3, so we're left with 2. Yes. Somebody is still holding on to the 4. Not anymore. Good. Right, but this should be familiar to you, right? So if you have light, there are 2 polarizations to it. Oh, laat maar. Oh, dat geeft niet. Yeah, so there are 2 polarizations, and these are exactly the 2 degrees of freedom that you can still choose in your vector potential. Very good. So we have 2 local degrees of freedom. So let's more explicitly look at what the solutions of this equation are and where these 2 local degrees of freedom appear. So then we have to be precise about the polarizations that one can have. Okay, so solutions. But this should not be too difficult, well, because it's simply a Klein-Gordon equation, except that now we do not have a scalar field here, but a vector field. So we have multiple components. Oops. And let's look at solutions in a bounded box. Because then it's slightly easier to write down the explicit expansion. So in a box with periodic boundary conditions. Periodic boundaries. So let's take a cube of side lengths L and volume V equal to L cubed. And we're gonna periodically identify the sides of this box. It's just easier than imposing some zero boundary condition. So the typical way we go about this to find an exact solution is first to look at the plane wave solution that satisfies these boundary conditions. So let's look at the plane waves. So this vector should, well, the plane wave, it will be of the form a wave vector k, and then an angular frequency. Let's write omega just for now. Okay, so this is a scalar, so we have to multiply it by some vector epsilon, which will be the polarization vector. So when does such a vector field satisfy Maxwell equation? Well, exactly when if I take out here like the four wave number, four wave vector, I guess, or at least the equivalent of the four potential in this case, then it should have a zero relativistic norm. Right, so this is saying that omega squared over c squared has to agree with squared norm of k. Right, because the D'Alembert, it brings down two of these omegas with an extra c squared, and then an inner product of k with itself. So it's useful here to now parameterize these plane waves by the wave vectors. And the wave vectors, of course, in order for this to be a periodic solution, they have to be 2 pi over L multiples of some wave numbers, some wave integers, u1, u2, u3. And then we'd simply take omega to be a function of this wave number. And it will be useful to always take it to be positive, where your k is really the length of the wave vector k. So that only gives one of the type of plane wave solutions where I have minus I times some positive real number times t. So I would like to add a plus or minus sign in front. Now I could just allow omega k to be positive or negative, but it's more useful to put a plus or minus around the whole part in the exponential. So in order to select one of these plane waves, I have to specify k as well as a plus or minus sign. And then I've covered all possible plane wave solutions. So why it's useful to put the plus or minus in front of everything here? Well, simply because then I'm going from a complex value to its conjugate. And we certainly want our vector potentials to be real numbers in the end. So we want to add one of these to its complex conjugate in a minute. Okay, but there are two more things that we have to satisfy in order for such a linear combination to be a well-defined solution. Well, the first thing is that we don't want the wave number to be equal to 0. So why is that? Let's do a quick poll again. Is it because such a term would not contribute in the expansion? Is it because it can be removed by a residual Gates transformation? Or does it not satisfy the periodic boundary conditions? Or is there some issue with 0-point energy here? Is there some divergence? So let's see. So there is a majority vote for a deep answer. I think the answer is a bit simpler than this. So at least one of you has chosen my answer. So what happens when I change my vector potential by a constant? Or if I change by a constant vector? What changes in the electric and magnetic fields? Right here, we still have them up here. Nothing, right? Because there are derivatives. So adding a constant to the vector potential, it does not change the physical fields. So this is residual gauge. Very good. So this is residual gauge. Or, okay, so the nu equal to 0 component in the expansion, you can just gauge it away. Okay. Now we're not quite there yet because now we've solved the Maxwell equation, but we still have to impose the Coulomb condition. So what does the Coulomb condition mean? Well, it means that the divergence, divergence of A has to vanish. So what is the divergence? Well, it brings down one of these wave numbers, wave vectors. So we get the inner product of K with our polarization, with a plus minus, and then this exponential. So what we really need is that these polarizations are perpendicular to the wave vector in order to satisfy the Coulomb condition. So now we can very clearly see what are these 2 degrees of freedom if I have my plane wave propagating in this direction. So meaning that if I take the unit vector in the direction of the wave vector, it's traveling in this direction, then I want my 2 different polarizations to span the space that is perpendicular to this. So let me take a basis of this space to be epsilon 1 and epsilon 2. So we're going to choose polarization vectors epsilon subscript lambda depending on our wave vector, where lambda is either 1 or 2, in such a way that the combination of these 3 vectors, so the 2 polarization vectors and the unit vector in the direction of the wave vector, form a orthonormal basis. Orthonormal. Well, let's be a bit more precise than just orthonormal. Make some space here. Oops. Go. Let's require that this basis is also right-handed. So what does that mean? Well, it means that these 3 vectors satisfy the right-hand rule, right? You know how this works. Okay, so as soon as we've chosen these polarization vectors, we now have kind of explicit basis of plane waves. I have to choose my k, I have to choose a plus or a minus, and I have to choose a lambda equal to 1 or 2. So to get the most general solution, I just have to add these all up. So general solution is now given by the following large expression. So I get a sum over all wave vectors. So let's be explicit. So they have to be 2 pi over L multiples of integers, but not vanishing. I have a sum for lambda, taking values 1 and 2. Then I have my polarization vector. And I have to take the plus and the minus component. So I have an e to the I k dot r minus I omega k t. Let's make it k. And also the other sign, so minus I. Like this. And then I can have arbitrary coefficients in front. So let's denote these coefficients by a subscript k lambda. But here, of course, I need to put the complex conjugate of that coefficient in order for the sum of this to be a real number. So this is to ensure that A is really a three-dimensional real number. But we'd like something more for this coefficient. We would like them to be dimensionless. So that's why I left some space open here to put some dimensional parameters in. I hope you also still have some space. So the convenient way to do this is to extract a square root of the omega here. And then we also have the volume that we can insert and the permittivity. Now you can check in this way that that we exactly these factors together give you the dimensions of a vector potential. So yeah, to make a k lambda dimensionless. And of course to make expressions later on simpler. Okay. So let's see what we have here. So we have these same plane waves, these same phase factors that we've seen in the solutions of the Klein-Gordon equation and the Dirac equation. So how did we interpret them there? So before, we interpreted this e to the I k dot r minus omega kt as a positive energy solution. Because well, if I take the time derivative, I get a positive omega coming down for the energy, while the other one It's a negative frequency solution, so we interpret that as a negative energy plane wave. So let's do a quick poll. Does this energy interpretation make sense here? So, well, maybe it's proportional to the angular frequency as we're used to, according to de Broglie. Or no, this is not quantum mechanics. There is no energy. Or no, this cannot be correct because we know energy is always positive. Or no, this is different from the energy that I actually thought was contained in the electromagnetic field. Some people are changing their minds, which is good. This is also again a bit of a trick question because there is no single correct answer here. But it's good that you thought about this for a bit. So in fact, all the no answers are very much defendable. Because remember, we're really doing classical electrodynamics here. So there is no de Broglie relation yet. So the yes answer is hard to defend. In classical mechanics, there is no reason why an angular frequency should have anything to do with energy a priori. Now, so certainly the first no answer, this is not quantum mechanics, is a very good answer. And since this is, if you like, classical mechanics, we know that the energy must be positive, or at least bounded from below. And if you recall, what is the energy stored in the electromagnetic field? I think this is something you computed, certainly in quantum mechanics, in electrodynamics or electromagnetism 2, I think, or even in 1. If you take some charge distribution, you can ask, well, how much work do I have to do to bring these charges together? And then you find out that you can compute this purely in terms of the electric field that you've produced by bringing these charges together. So the work you've done is actually stored in the electric field. And what was this answer? Well, the answer was that the energy stored in this system, it can be simply expressed in terms of the electric and magnetic field. So for the electric field, we found there was just the square electric field integrated over our box. But you can also store energy in the magnetic field. There, just look at the norm of the magnetic field. So this is the energy that you have derived before, purely classically. Right, clearly this is positive. So this cannot agree with our previous interpretation. So really this quantum mechanical interpretation we had before is absurd here. Because we have a perfectly well a definition of what energy is in this classical setting. And it's not the one that we assigned a negative one to this particular plane wave solution. No, it's just given by this explicit expression here. So this is not quantum mechanics yet. We know very well what the classical energy is. We are working in terms of the vector potential. So in terms of the vector potential, we can write this as the time derivative squared and the curl squared. Now, this particular realization, it really allows us to change our perspective on what quantum mechanics, where one might be able to find quantum mechanics in all these nice relativistic wave equations. Based on this particular example in terms of electrodynamics. So this wave equation, the Maxwell equation, well, it's clearly not the wave equation of a wave function. It is the wave equation of a classical field. That is this vector potential. Or if we did not remove all the gauge, then it was this fork potential. So clearly we have not done any quantization here. We still need to quantize. And what we'll see is that this will also be the resolution for the particular case of the Klein-Gordon equation and the Dirac equation. We were trying to force our quantum mechanical interpretation on this relativistic wave equation. But really what we're going to observe is that no, these equations, they're not quantum mechanical equations at all. They are the classical equations for the fields that we still need to quantize. And then they will actually describe these quantum particles. Spin 0 in the case of Klein-Gordon, spin 1/2 in the case of Dirac, and here spin 1 in the case of electromagnetism. So we're not nearly done, because now we're only going to start doing the quantization now that we have the wave equation. And this we'll be doing next week. So really, what does it mean, quantization? Well, it means that we take, for instance, our Hamiltonian, and we want to turn it into an operator working on some Hilbert space. So what are the degrees of freedom in this system? Well, if we're working in this particular expansion, it is really these coefficients in front of these Fourier modes. So the Hamiltonian explicitly is a function of these AK lambda. So what we're going to do next week is we're going to try to turn this into an operator that will just be the same function you have here, but where now these coefficients have actually become operators. And we'll exactly interpret these AK lambda operators, and the particular notation that we're using here is quite suggestive, I think, given the first half of this course, as creation and annihilation operators in a Fock space representation. So that's where we'll be going next week. And we'll actually make sure that this is a very well-defined operation by showing that actually this Hamiltonian in terms of these coefficients is nothing but an infinite sequence of simple harmonic oscillators. that we perfectly know how to quantize. Okay.